In this video, we're going to be talking about computation problems, and these are problems like this where you have to find the value of these large expressions. So let's get started. So here we have this large number minus the product, 2 times the product of these large numbers, and then we square another large number. So the strategy for these problems is to just assign numbers to variables so you can see manipulate different factorizations, sum of cubes, difference of cubes, difference of squares, sum of squares, the fourth power factorizations, etc. So we have 2012, 2011 minus 2 times 2012, 2011 times 2012, 2009 minus 2012, 2009 squared. So here I can just assign a variable. So I'm going to say x equals 2012, 2011. And what else? I see this is y. I'm going to say y. The value of y is just this number right over here. 2012, 2009. So if I rewrite this expression, I get x squared minus 2xy plus y squared. And this can be factored as x minus y squared. So now we just see just x minus y squared. And it's that simple. We just take the difference of these two, 2012, 2011 minus 2012, 2009. The difference of these two is just 2. And we get 2 squared as our answer, which is 4. So our answer to this problem is just 4. And that's how you can basically do almost any of these problems by just assigning variables to find factorizations. If you have division, like if you have like a division problem with like large numbers, try to factor, like pull out a common factor and then divide it out. But when you have no division, this is how you do it. Okay, let's move on to the other example. So this one comes from the 2011 state sprint number 30, so it's the last one in the state sprint, so it's the hardest one on the state sprint. So what is the value of 52683 multiplied by 52683 minus 52660 times 52706? So we use the same strategy, variables. We can set x equal to 52683. We can set y equal to 52660. And we can set z equal to 52706. Now let's rewrite this expression. We have x squared minus, then we have 52660, which is y minus y times 52706. So it's x squared minus yz. Now I have this expression, x squared minus yz. I don't see how to factor this. I can't really factor this expression. And then we're stuck. So whenever you throw in variables and you're stuck like this, try to redo the variables. These numbers are all close to each other, right? So another tactic is to rewrite everything in terms of a number. In this case, we're going to pick x, 52683. So if I pick x as sort of I'm going to erase this because this expression is not going to help us do the problem. So now our second strategy is to rewrite everything in terms of x. We have x times x is still x squared, right? This expression is x squared minus. Now we need to rewrite it in terms of x. And now when you subtract these, y is 52660. This is just 23 minus x, so, or x minus 23. So minus x minus 23 times, Then over here, we have z. Z in terms of x, if we subtract these, we get 6 minus 3 is 3. You have the 10 carry, because you have to borrow, so 10, 2, so you get 23 again. So the difference is 23, because then these all just become zeros, because 7 becomes a 6, and then the rest stay the same, so it's all 0. So this is x plus 23. It is more this time. And now we can see a clear pattern. This is the difference of squares factorization. So this can basically, we have the factored form, but that won't help us evaluate this expression. We can just put in x and y, and that won't help us. So we need to expand this, so we can easily expand this. So you have x squared, right, minus 23 squared. It's minus the whole thing. Expanding again gives us x squared minus x squared plus 23 squared. These cancel. The x squared terms cancel. We're just left with 23 squared. Now, instead of multiplying it out again, we can just use the expansion for the square of a binomial, and we get 20 squared is 400, plus 20 times 3 is 60, 120, plus 9, 400 plus 120 is 520, plus 9 gives us 529. So our answer to this problem is 529. And we see that just by throwing in variables for different values, we can easily evaluate expressions like this.